Looks like there's a question, so let me take a look at that. Oh, I love the penguin, Blair. Thank you. That brings a smile to my face. Very cute. Okay, so I want to get started. First of all, I want to ask you all a question. Have you had any problems getting into Teams? If you have, could you please just kind of tell me about it? I think there's been I asked my previous class today, and there was somebody that had a quirky thing happen, but was still able to get in. Thank you, Luke, for your response. So if you have an issue, please let me know what it is, because the sooner I know about it, the better. If it is actually an issue that I need to talk to our IT folks about at NWAC, I just would like to know. So let's talk about Alex for a moment here. So I'm looking at your course right now, and as a class, you've got credit for 80 topics, having learned 80 topics as a class, which is quite good because there are 179 topics in the course. Divided by 2 is 89.5, is about 90, is about half of that. So we're pretty close to that, which is great because we are getting really close to the halfway mark in our semester. But what I wanted to take a look at is the direct classroom instruction. I often look at this report to see how the class is doing. We've got an objective due tonight on function combos, and we still have one more topic, actually question in a topic that we want to cover in that objective, which I will do here in a short while. And this is the objective that's due tonight. And I would really encourage y'all, if you want to do students who tend to do the homework as soon after class as possible tend to do better in the class. I've seen that for many, many, many years. I've been teaching for, I'm not sure I want to admit that, but I've been teaching since I was a grad student back when I was in my early 20s. So I've been teaching for a few decades now. And students who are able to work on the course as soon after class as possible is really the best way to do it. I did it both ways when I was in college, and I struggled when I waited until the last minute to do my homework. The next semester, I committed myself. This is when I was a freshman. The next semester, I committed myself to doing my work as soon after class as possible. And you know what? I did it. I did that. And I had more free time and got better grades when I did that. So if that's something you really want to think about. It will be less stressful, I think. It certainly won't be more stressful if you work on it as soon as you can after class. You're more likely to remember what we talked about in class, and then you work on the problems, and then you're more likely to retain the material over the long term, which is what you really need to do as the final is comprehensive. So there's that objective that's due tonight. This is the objective that we're going to work on today. I should see some zeros in here because some of these topics are probably, if you're oh, gee, we got a lot of feedback. Yes. Thank you. Okay. So these should be new to, some of these topics should be new to you because they are more challenging topics topics you haven't seen before. We've got this test review objective that's coming up before our test 2, which is 1 week from today. Your test 2 is 1 week from today. And you will see tomorrow I've devoted to announcements, to make announcements in all of my classes tomorrow. And so you will see some announcements from me tomorrow. And certainly the testing violations, I did not give out penalties for the first test, but I will for the second, third, and the final. So it's very important that the picture of your government issued photo ID is vital. You can't send it to me after the test. The point of that is that you have it taken immediately before the test. So you want to make sure you're taking a picture of it and that you get your first and last name on that picture. And that is so important. Otherwise, I can't ID you. So I'm going to practice some more and do some more testing in ALEKS, because from what I've seen of ALEKS in the testing, you can go back and redo almost any of those pre-check steps. And I don't need a picture of you on exam day. What I really need is a picture of your government issued photo ID. So when you hold that ID up to the camera, I love to see your faces, but what I really need to see there for testing purposes is just a picture of your government issued ID. So have it fill that space. Stand back farther or stand up closer to get it to fill that space. So what you're seeing down here, test 2 review objective, you can see that some of the scores are pretty high for some of those topics. And that's because every topic in the test 2 review objective is one you've already seen before and quite possibly got that topic and have maintained that by taking knowledge checks. Those knowledge checks are very important to study for those as if you would a test. That's another way to retain the material. So it's one thing to learn a topic, it's another thing to retain the learning of that throughout the semester. So it's probably something that I would encourage you all to think about. Students who have used those knowledge checks in ALEKS has studied for them like tests, tend to do really well in the course. And I haven't really changed the course much over the last several years. So all of these topics, except for what we're going to do today that are in here, I've already presented those topics in our course. So that's why they're appearing here. Now you should see very soon, if you haven't already, the ability to work on the test 2 review no credit assignment. If you have not learned one of the topics in here, ALEKS is not going to show it in your test 1 review objective when you do that for an objective for ALEKS credit. It's not going to show it in there. So the only way, if you have not learned all 25 topics, that you can see them all to prepare for test 2 is by doing that test 2 review no credit assignment. That's where you will see them all. So anybody have any questions on anything that we have talked about so far? So there was one question in one topic that I didn't quite get to last time. That topic is due tonight with the other topics in that particular objective. Let's go and look at that topic now. So I'm going to go down to this document and I've got it ready to go. I had a student in the last class today say, gee, I love that topic. And then I had to ask, and he said that in the chat. And so I had to ask him, well, which one were you talking about? He said this one. And that's because I like complex problems. Well, I'm like, oh, that's good. I'm glad you like that problem. So let's talk about this problem. This particular topic finding a difference quotient for a linear or quadratic function. You will see this as one of your written work topics on test 2. That's because business students, those who are taking Survey of Calculus, those students who want to go to the Walton, get into the Walton School of Business, they will take Survey of Calculus, and this comes up in Survey of Calculus. It also comes up in Calculus 1. So it's important for us to teach it in college algebra. College algebra is, according to the state, a gateway course, which means students take this course. It's transferable to other institutions in the state, but it has to serve many purposes, including considering what math courses students can take in the future. So let's take a look at this topic, finding a difference quotient for a linear or quadratic function. Find the difference quotient, which is f of x plus h. That h means a little bit more. It's not important to know it in this class, but it really is important to know it in calculus or Survey of Calculus. What we've learned in this class is we've talked about average rate of change. What's your average speed going from Bentonville to Fayetteville on the highway? Now, what happens if a policeman comes along, uses his radar gun to clock somebody's speed? That is an instantaneous rate of change. That is a rate. He gets your speed at a specific instance. This right here represents an average rate of change. In calculus, part of what we study in calculus are what are called limits. And a limit of average rates of change is an instantaneous rate of change. So that's where we're really going with all of this. We're just laying the groundwork. So we want to find this difference quotient. We have a difference in the numerator, and because division is involved, we have a quotient. Of course, we can't have the entire denominator be 0 because that would cause division by 0, which is undefined, which is why we have this restriction right here. So we want to find the difference quotient for the function below, specifically for this function right here. F of x equals negative 2x squared plus 5x minus 6. Now, since we've got f of x plus h and f of x, this x really here is acting as the word input. So I would encourage you to take out the x's and replace them with the word input. It may make it seem like it makes more sense to you. So for this x, I want to put in input. For this x, I want to put in the word input. For this x, I want to put in the word input. And now, rather than having it as f of x, where you see an x inside here and you see x's on this side, this can be quite confusing for students. You don't see an x inside the parentheses anymore. You see the word input. So just to figure out what you need to write down next, it's probably a good idea. So for each one of these x's, for f of x, we want to take that x out, replace it by the word input. X is really the input when we're talking about ordered pairs, and y, the whole thing, is the output. So that's why we can replace x by the word input. Here, here, and here. So what does this give us? This gives us f of input equals negative 2 times x, which we're using the word input to denote x, squared, plus 5, here's an x, we're putting an input for that x, minus this 6. And that's what we're going to work with. Now, what do we want to find? We want to find the difference quotient, this right here. We can break this down into 3 parts. First, we can find this f of x plus h. After we find that, we can then subtract off f of x. After we find this difference here, we can then find the entire quotient by dividing by h. So we know this is a way we can write our original function f using this. Our first step we want to do is find f of x plus h. So now this x plus h is inside those parentheses, and therefore that x plus h inside those parentheses is our input. So let's put that in for the word input. So we're going to put x plus h in for this word. Well, actually also for this word input, this word input, this word input. So we get x plus h equals -2, put in x plus h here, x plus h squared, plus 5, here's input, put in the word x plus h, minus this 6. And now we just want to work with this before we don't want to write down too much. We just nice progressions here. This is what really tends to throw students here. But we've done a lot of expanding binomials in this class. This 2 tells us how many of this base to multiply together. It's mathematicians, exponents are mathematicians' way of writing shorthand for repeated multiplication. This tells us that we are to take 2 of this base x plus h, 2 of them, that means x plus h times x plus h, and multiply them together. So we're taking x plus h and then x plus h again. So now we have a binomial. We have 2 terms times 2 terms. We can FOIL. That's the one and only time you can FOIL is when you have 2 terms times 2 terms. We can FOIL here. The first 2, x squared. We have the outer 2, xh, and the inner 2, hx, which we can switch and say it's xh as multiplication is commutative. It doesn't matter the order. So we get 2xh plus h times h, which is h squared. So we want to take this out right here, all of this out, including that square, and replace it by x squared plus 2x h plus h squared. So we're going to take that out and replace it by this right here. We still have the -2 in front, and we still have all of this at the end. So now what could we do? Can anybody tell me what should we do? The hint is we have multiplication over addition here. So we could distribute that -2 through. Sometimes in math, it's about what can we do? If we don't know what to do, it's what can we do? And try that. Trial and error is a great way to learn math. I've learned so much math by trial and error. So it's great. So let's distribute this -2 through. -2x squared. Right there. -2 times +2 is -4. -4 of what? xh. -2 more precisely, is -2 times h squared is -2h squared. Plus, this is multiplication over addition, so we can distribute the 5 through. 5x plus 5 times h, copy over the -6. Now, we're done. We can't combine any like terms, and it has a way of reviewing. Like terms are terms that have the same variable portion to the same exponents, and we don't have any of those. This variable is x here, it's h here. There aren't any other terms with xh in them. So we don't have any like terms that we can combine. So when we get to that place, the next step is to now we found f of x plus h. We want to subtract off f of x. And Since this is going to be a written work problem, I expect to see the correct notation. So the rubric that I have in Canvas requires the correct math notation. So I encourage you to reread all of those testing announcements in Canvas just to be aware of all the testing violations and also what's required in the testing experience. It's a good time to review that and to thoroughly understand that so you have time to ask me questions about that on Tuesday. So we are now going to, I took this and I said, well, I can't do any more. So meanwhile, I'm just going to put in minus f of x, which is what we need to find here. And I'm going to, and that means we're going to subtract off. So I put the subtraction sign here, f of x. Now f of x, if you scroll, if we go back up, is just stated right here, f of x. It's negative 2x squared plus 5x minus 6. So I copied that down inside the parentheses here. And now let's see what we can do. So I just copied all of this, just making sure I copied all of this down to here. And now I'm going to distribute the minus sign through. Let's distribute this minus sign through. It's going to change the sign on each term inside the parentheses. So negative times negative is a positive 2x squared. You see that here. Minus 5x. See it right here. Minus a minus, which is a plus 6 right here. Now we're going to cancel. Okay, we're going to cancel. But when you're canceling on the test, when you show your written work, because you're going to see this topic, you want to make sure you're canceling so I can see the number underneath clearly. So you might want to write, before you cancel, you might want to write darker and cancel with a light mark so I can see it. If you cross, sometimes have students who cross everything out and I can't see the expression underneath, and I can't give you credit if I can't see the expression underneath. So the way to cancel here, the best way is usually to go from the end. We've got a 6 here. Gee, wouldn't it be nice if we had the opposite of adding 6, which is subtracting 6, which we do because that sums to 0, and 0 plus what's left is what's left. So we can cancel the 6 with the minus 6. How about this minus 5x? Gee, it would be nice if we had a plus 5x because they would cancel. Well, we do. So they cancel. This plus 2x squared, the opposite is minus 2x squared, which we have, so those cancel. So I need to clearly see your cancellation. You don't want to assume that, for instance, this plus 2x squared here might be plus 2x squared here because you might forgot the negative sign. You don't want to just assume you can cancel them. You really want to check that your signs are correct. So you're likely to get more credit if you do that. So what we have left, we have we've got this term left which has an h in it. This is plus a negative, so this is a term, it has an h in it, and this term has an h in it. So let's factor that h at one h out of all of those terms before we proceed. So we're going to factor an h out front. Then we're going to go term by term. That single h came out, so we're left with negative 4x. Right here, we have minus 2h squared. Now we really have h times h. 2 h's means h times h. We're only taking one of those h's out front, so we really have an h left. So we really have negative 2h left. And then down here, we took this single h, we factored it way out front, and we have a plus 5 left. So that's what we have here. Now the last step we need to do is divide by that h. So we have this in the numerator, divide by h. H divided by h is 1. 1 times what's left is what's left. What's left is this. I just copied it over here. This is the answer. Negative 4x minus 2h plus 5. Any questions on this last topic in the objective that is due tonight? I already did one in this topic last time, but I wanted to do a more challenging problem today. I didn't quite have time last time to squeeze this one in, and as you probably can see, that would not have been wise if I'd even tried to do it in the little time we had left. Any questions on this topic? You know you're going to see this topic on your test, so please feel free to ask questions about it.
I have a question.
Yes.
I got kind of confused on after you distribute the -2 and the 5.
-2 and the 5. I'm not sure where we're at. Are we at this f of x plus h? Are we at this? Or
The
are
second one.
This one?
Yeah, I was confused when we got there.
Okay, so where is your confusion where this came from?
Where the negative was distributed out.
So here, how to do this?
Yeah.
So this is a negative. So a negative is really a -1. Okay, so you're really taking and multiplying every term in here by -1. So a negative in math represents a -1.
But how did where did that equation come from?
Okay, I'll show you in 1 second. Let me just make sure I get back to. Okay. This right here, after we finish with f of x plus h, we then have to look at the next part of the process. So we are asked to not just find f of x plus h, we're asked to find f of x plus h minus f of x over h. So we can't do any more with finding f of x plus h now. So we move on to subtracting off f of x. Now this f of x is right up here. It is -2x squared plus 5x minus 6. Does that answer your question?
Oh, yeah, okay. I get it now.
Well, it's good. I'm so glad you asked the question, because I bet there's another student or 2 or 3 in the class that didn't understand that either. So do you have another question, or feel free to ask another question just to make sure you understand how to make all of the connections. Are you good? Or do you have another question?
I think I'm good now.
That's good. Well, anybody else have a question on this problem before we move into the next objective? So let's move into the next objective. I'll leave that one up just in case we want to come back to it. So we are looking at objective 12 now on inverse functions. So really where we're going in this course now is we're getting ready to talk about logarithms. I find when I do it earlier in the semester, students catch on more, and it's not at the end of the semester where there's so much work that's due and everyone's so burnt out. So objective 12 is on inverse functions. So let me first start by explaining what a function is. Let's ignore this word inverse for now. Let's look at just what a function is. And what a function is for each x, really, there is exactly one y. But in order to understand and keep consistency with the definition of a one-to-one function, we have to state it a little different. So a function is what's required for a function is encircled in purple here. So for what's required for just a function is for each y, there is exactly one x. So for each y coordinate that we have on our graph. There is exactly one y coordinate that it came from. That is what a function is. We don't even talk about inverse functions if we don't start with a function. So we need to have a function. For each x, there is exactly one y. You might have seen that in the past. You can also state that as for each y, there is exactly one x. Now for an inverse function, this is required, as is this statement. For each x, there is exactly one y. So for each y, there is exactly one x, and for each x, there is exactly one y. There's this nice one-to-one correspondence. So for each y, there's one x, and for each x, there's one y. You're never going to get, you're never, for example, for each x, you're not going to have two y's that it goes to. And for each y, you're not going to have two x's that it goes to. So required for a function is just what's encircled in purple. Required for a one-to-one function here, in order for the function to be one-to-one, it's assumed that you have a function, and so you have to have this, and you also have to have this. You have to have this nice one-to-one correspondence. And to give you a sneak peek at what that would look like, this is what it would look like. Each number, each x to each x corresponds one y. For each of these x's over here corresponds one y over here. So this is the x, these are the x's, these are the y's. Each x goes to one y. And you can see that. Now, also, each y corresponds to one x. So if you go backwards, you just get one number. 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 You go forwards in this direction, you just get one number. You just get one number. You just get one number. One number, one number. And I didn't mean to sound like a broken record, but I think hopefully you're getting the point there. So this is what a function diagram would look like for a function and its inverse. And we will talk more about that diagram in a bit. Let's go back here. So I want to mention the vertical line test and now the horizontal line test. The vertical line test tests to see if you have a function. What does the vertical line test say? It says if you can draw a vertical line anywhere through your graph that intersects your graph in more than one place, you do not have the graph of a function. So that should be something you've all seen before. Horizontal line test is very similar to the vertical line test, although it doesn't, you don't look at a vertical line, you look at a horizontal line. So horizontal line test to see if the function that you already have is a one-to-one function. In other words, for one x, there is exactly one y, and for each y, there is exactly one x. A horizontal line test states that if you can draw a horizontal line that intersects the graph in two or more places, then you do not have the graph of a one-to-one function. Why do we study one-to-one functions? One-to-one functions are the only functions whose inverses are also functions. We like to work with functions in college algebra. So we want to only be working with functions for the most part. Where we're going now is we're starting the section, the chapter, really, if you want to look at it like that, on logarithms. And exponential functions are inverses of logarithmic functions. And functions which are inverses of one another have a lot of neat properties that we can use. So that's why we study them. So if you can draw a horizontal line that intersects the graph in two or more places, then the function is not a one-to-one function. We're going to do a problem on that in a moment or two. Let's first explore this diagram more, or what I'm trying to get across in this particular page of notes. One of the issues, and believe me, I don't have many. I really like ALEKS a lot, and their support is top notch. You know, I've had students in the classroom, I forgot my password. I'm like, well, I can give you your ID, your login, but I can't give you your password. They get right on the phone with ALEKS, and within 5 minutes, they have it reconciled. It's not necessarily like other software companies. ALEKS is really top-notch support, and I really like them a lot. But one of the issues I have with ALEKS is they don't give an overview of a particular objective, but they really can't because of the artificial intelligence nature of it. And this course is based on a book who that author, the videos from that author are available in your ALEKS course, but I'm not too wild about some of her overview videos. So it's important, and I will put these notes in ALEKS right after class. You're going to see likely more notes now because we're getting to the stage where the review from previous math courses is going to be less and less. So I wanted to look at this function diagram here. And also I want to point out a few more things. But first of all, the very first thing I want to point out is this right here in this circle. Well, it's more like an ellipse, really. In here is the domain of the function f. These are x coordinates of the function f. And this is called the domain. The inputs are all, remember, domain is a set of all x's. Range is a set of all y's. So this is the domain of f. This is the range of f. If I take -2 and plug it into x here, because this is an x, right? -2 is an x. If I take -2 and plug it in for x here, cube means we want 3 of those -2's. Remember, exponents are mathematicians' way of expressing repeated multiplication. So this says take 3 of what? Take 3 of the x's, which in this case is -2, and multiply them together. So we want -2 times -2 times -2. -2 times -2 is +4 times -2 is -8. So this -2 in the domain gets mapped to this -8 in the range. This -1 goes in for x. We have -1 times -1 times -1. 3 of them multiplied together. An odd number of negatives makes the answer negative because they can't buddy up. So we have -1 times 1 times 1 is 1. So we get -1 is mapped to the same to -1. If we cube 0, we have this x right here. It's put it in there. We get 0 times 0 times 0, which is still 0. So 0 gets mapped to 0. If we find 1 times 1 times 1, that is 1. 2 times 2 is 4 times 2 is 8. So that's how the mapping occurs. Now let's say what if we wanted to make this set the x's, or you could also call it the inputs, and this set the range or the outputs? Well, we can. The opposite of cubing is actually cube rooting, like this, cube rooting. We write it like this. It's like a square root, but we put this 3 in the V. We don't put the 2 in the V for square roots because we use them all the time and it's just understood to be a 2. But once we talk about cube roots and fourth roots and fifth roots and so forth, we put that index, it's called an index, in that V. So if we go, when we went in this direction, we were cubing, we need to do the opposite to have this be our starting set and this be our finishing set. And the opposite of cubing is cube rooting. So let's now, when we go from here to here, we're using the cube root function. This is the domain of G. Let's call it G because we called this one F. Let's call the function we are talking about G. So this right here, this is the range of the F function, but it's the domain of the G function because we can go backwards. And when we talk about domain, we're talking about x's. And if this is the domain over here of the x's, the range of G are the y's, they would be over here. Those are the y's. And we'll work with that in a bit. But before we do that, I want to explain the importance of ordered pairs. We have so many ways of writing ordered pairs in math. One way is by using a function diagram. Let's go back to considering this as the f function here, and this is our domain, our set of x's. This x, -2, corresponds to a y of this function of -8. So -2, -8 is an ordered pair, which means we could put it in a t-table. A t-table like this is just a table of ordered pairs. And we'll come back to this in a moment. We could also write out the ordered pairs using set notation. So for instance, F is going this direction because G is going the other direction. We can use set notation. So f of x equals, in set notation we use braces, -2, -8. It's that ordered pair. We use comma to separate elements of sets. The next one, -1, gets mapped to -1. Comma. 0 gets mapped to 0. 1 gets mapped to 1. 2 gets mapped to 8. And then we've got the necessary commas and we use a closing brace here. So we could write out f of x as ordered pairs in that way. And you'll see this in ALEKS, which is why I'm talking about it. G of x, on the other hand, we start in this set. We start over here. This is the domain of G of x. So we could now go this direction and write down our ordered pairs. -8, we're starting with the x of the G function, which is -8, -2. And we could do all of those until we got to 8, 2, which is down here. Now, what's really going on with the ordered pairs between F and G? You can see that their coordinates are getting switched. The -2 is in the x here, but it ends up in the y here. It's in the y here, but ends up in the x here in the G function. And when we switch -1 and -1, we still get -1 and -1, and we switch 0 and 0, we still get 0 and 0. 1 and 1, we still get 1 and 1. When we switch these two, we get 8 and 2. So our x and y coordinates are switching when we consider inverse functions. So whatever function you're talking about, in the inverse function, whatever it's called, the x and y switch. That's what I want you to get out of this. So I think that's important. So we've got three ways here of seeing ordered pairs. You can put them in a T-table. All of these, as long as you've got your X and your Y's correct, depending on which function you're using at the time. These are ordered pairs. You could view these as ordered pairs, and you can view these as ordered pairs. So there's different ways to view ordered pairs. And why am I talking about that? Because the graph of every function out there is composed of points, each of which has an ordered pair associated with it. That's why we talk about them, and that's why it's so important to understand all of the connections. So let me see what I'm talking about here. I think I got to see what else I've got. I think I did something. Yeah, I'll do that later then. Okay. So I think we're good here. Now, I will prove to you shortly that the inverse of f of x equals x cubed is indeed g of x equals x cubed, or sorry, g of x equals the cube root of x. Now, one way to prove that is this. If you take the composition in either direction, which we've already talked about that, you're going to get back x for both of them. If you do that, that means that the two functions are inverses of one another. Two functions are inverses of each other if f of g of x equals x, and also both of these conditions must be true. G of f of x equals x. So let's try it for the two functions that we've been working with. It's likely to be given to you in this form, this fog form, if you will, here. That open circle doesn't mean multiplication. If we want multiplication, it's always colored in. It's not multiplication, it means composition. So the first thing is to change that to workable form. It's f parenthesis, g parenthesis, x. Close off the parentheses. We did some of this last time, converting like that. This one, on the other hand, is g parenthesis, f parenthesis, x. Close off the parentheses. So let's see if we can get the composition in both directions being equal to x. What's the g of x that we've been using? We go inside parentheses first. G of x is cube root of x. So I want to take out the g of x down here, and in its place, put in cube root of x. That still leaves the f parenthesis over here and this outside parenthesis there. How do we find f of this? Well, where's our f function? And we need to see what we need to do with f. F is right here. It takes, what does this do? It takes whatever's in parentheses and cubes it. What's in parentheses down here? 3 root x. So we have to copy that down and then cube it. And what happens? This cubing undoes this cube rooting, and we get back x. So that's what we need to have. That's the first requirement down here that we need to have in order for two functions to be inverses of one another. We need both of these requirements, though. So we converted this to workable form. We want to first, in this case, do what's in here, which is f of x. So let's go find out what f of x is. F of x is x cubed. So I'm going to take out the f of x down here and replace it with x cubed. We still have g parenthesis and then this closing parenthesis. Well, what do we have to do here? What does a g function tell us to do? Our g function tells us, what does it tell us that we do with now? We have to take whatever's in parentheses because this x is in parentheses. Take whatever in parentheses, and what do we do to it? We take the cube root of whatever's in parentheses. What's in parentheses down here? X cubed. And we copy down that x cubed because that's what's in parentheses, and we cube root it. And we get back x. So cube rooting is different than, say, if we worked with, say, x squared, and then working with x squared. Odd roots are nicer to work with than even roots, like the square root or the fourth root. Just keep that in mind. So I think we've done everything we want to do on this page. Just notice right here what happens with the x and y coordinates. They get switched. -2 gets switched, so it's x here, y here. -8 here, which is y, gets switched. The -8 now becomes x. So with the function and its inverse, that's what happens with the ordered pairs. The numbers get switched. So I think I've covered what I need to cover there. Let's take a look at this page. These notes are not, I will put my personal note, put these notes in Alex after I get done here, but you won't find these notes any other place in Alex unless I put them in there. So that's why I'm doing that. They're available in instructor resources on the main menu, or they will be. So rather than using F and G, sometimes we use this inverse notation, and you will see this in your problems. So I've got f of x here. Instead of G, we can write F inverse. Now, this doesn't mean -1. It's written like that, I know, and it's a bit confusing. But it doesn't mean find the reciprocal or anything like that. It means this means, first of all, that it's related to the f function, and it means we want to find the inverse of the f function. So this f of x and this f inverse of x are inverses. Do you have a question? Feel free to ask questions. Just unmute your mic and say, I've got a question. So f of x and f inverse of x are inverses. Now this is read right here. It's read f inverse of x. This doesn't mean -1. It means inverse. This right here means the word inverse. That's shorthand for the word inverse. F inverse of x. So rather than using the F and G notation that we're using, let's now use the F and F inverse notation. So I just replaced G of x with F inverse of x, and G over here with F inverse over here. So we're still getting that we need to, in order for two functions to be inverses of each other, we need to have this be equal to x and this be equal to x. So in both directions, you need to get x in order for two functions to be inverses of each other. Now next, we are going to be algebraically finding the inverse, which we just did in the previous problem. And I'm going to use this method of doing so you can relate to it, since we just did the problem with f of x equals cube root of x, and we're going to convert that so you can see the process in action. But in a nutshell, you might want to copy down this, how to algebraically find the inverse. You're going to see one of these has a written work problem on your next test, and it's not going to be quite as basic as the one we're going to do first. I'll show you which one you're going to see when we get to that problem. So how do we algebraically find the inverse? We take out f of x and replace it with the letter y. That's the output we're used to working with. And then we need that switching going on that we saw in the sets where that switching went on. So you want to replace y with x. You know how the y coordinate became the x coordinate and the x coordinate became the y coordinate? We want to replace y with x and x with y. Solve for y. And then when we're done, we want to take and replace that y by the inverse notation, f inverse of x. And I will need to see all of those steps to get full credit for the written work problem. So let's do that for f of x. I took this out of the previous example. F of x equals the cube root of x. So we could see this in action. First thing we want to do is take out f of x or g of x, h of x, whatever your function notation is, and replace it with y. So I put the y down here. Now we need the switching step, and that is we replace y with x and x with y. So here we see y. We want to replace it with x. And right here over on this side, we see cube root. We see an x, and we want to replace it with y. And if you see more than one variable of say x or y, you want to replace it. You want to replace it each time. I don't think you're going to see that, but I'm not 100% sure because I can't see every problem in ALEKS. Their software is so complicated. I mean, they got a National Science Foundation grant to work on ALEKS, and they had people from all over work on it. Cognitive scientists, psychologists, mathematicians, people really good in computer science. I mean, it was a remarkable piece of software compared to what else I've seen in math. So we replaced y with x and x with y. So this x got replaced by this y. Now, solve for y. The opposite of cube rooting is cubing. So we want to cube this side. Therefore, what we do to one side, we need to do to the other. So let's take this x and cube it. Solve for y now. This cubing undoes this cube rooting. So we just get y. And we copy down what's on this side. And lastly, we take out y and replace it by f inverse of x. So we took out this y, replaced it by f inverse of x equals, and we just put the x cubed on the other side. So that's how the process works in a nutshell. It will get a little bit more complicated, the one you see on the test, but I will go over one of those with you shortly. And I'm just now going to jot down the time our class ends. It ends at 1:50, so I can keep looking, maybe glancing over there a few times so I won't forget. So now we are to the stage where we want to start looking at some of the topics in this particular objective. So you can see there's really a lot going on. It took me basically an hour just to talk about that. And it's really important to understand all of those connections. The more you understand connections between different topics and so forth, the more likely you are to retain the material. And retention is a big part of being able to be successful in a math course, especially when there's a comprehensive final involved. The comprehensive final in this class is worth 20% of the course credit. And just to give you an idea of how much that is, there are about 600 points in this course. It's worth 120 points. So and I am required by our department at the minimum to make the comprehensive final worth 20%. Some faculty members make it worth more. So I'm really hit the bottom of what I can do. So let's take a look at the horizontal line test. It works just like the vertical line test, except that you use a horizontal line. And what we're concerned about here is whether we have a one-to-one function or not. And the one-to-one nature of a function really looks like this. If you go this way, you get this one-to-one correspondence like this. You go the other direction with the inverse function, you still get a one-to-one correspondence. So you just have one, you don't have like a line going from this -2 to this -1, for example. So it's nice one-to-one correspondence. So for each function graph below, state whether it's one-to-one. In order for a function to have an inverse, which is also a function, you must have a one-to-one function. And what needs to happen is that graph of that function needs to pass the horizontal line test. And if you're familiar with the vertical line test, it works the same way, except you use a horizontal line. So what I'm looking at here is I want to imagine drawing horizontal lines and asking myself, how many times is that going to intersect the graph for each horizontal line I draw? And that's one time. If I draw a horizontal line here, it's one time. If I draw a horizontal line here, it intersects the graph only once. Or up here, it intersects the graph only once. And pretty soon I realized if I did that for the rest of my life, I would find out that the graph is only going to be intersected one time. So the answer for this is it passes the horizontal line test, and therefore the function is one-to-one. So I answered yes. Moving along to the next graph that Alex gave me, it's a upside down absolute value function. There are many places where I could draw a horizontal line that intersects this graph in two places, right here and right here. That fails the horizontal line test. And therefore, that function is not one-to-one, so the answer is no. This also coincidentally fails the vertical line test. Does it? No, let me see about that. I may have to eat my words there. Does it fail the vertical line test? No, it's good, because if you start drawing vertical lines here, yep, you're good. It's a function, the graph of a function. If you had an absolute value function the other way, well, actually it would be a function. It would fail the vertical line test if you had one open like that. So I really have to think about that just to be clear. This is a graph of a function. They even say that for each function graph below. But it fails the horizontal line test and is therefore not one-to-one, so the answer is no. This is a cubic function. So does it pass the horizontal line test? The answer is, could I draw horizontal lines for the rest of my life and it only intersect the graph in one place? The answer is yes. So this function is a one-to-one function. And the answer is yes. Down here, this open circle means the point is not included. If the point were included, it would be written in black. It would be colored in black, like this point is included. This point is included. This one is included, but this one is not. So I could start drawing horizontal lines. No problem, they intersect the graph in one place. But what happens here, this point is not included. So when I draw the horizontal line here, this point is not included, so we're okay. But this one is, we're okay, because that horizontal line only intersects that graph in one place. Then we can keep drawing horizontal lines down here and see that we're okay. And so this is a one-to-one function, so the answer is yes. These two over here, and let me just read what I have here, and then we'll go back and look at the last two. If you can draw a horizontal line that intersects the graph in 2 or more points, the function is not one-to-one. Okay? So here's a horizontal line that intersects this graph in 2 or more places. That function is not one-to-one. So the answer is no for it being one-to-one. This one-to-one, they remind us what we're doing there. What about this one? There's lots of places I could draw a horizontal line and that intersect this graph in actually an infinite number of places, since this is going to go back and forth forever. So it certainly intersects the graph in 2 or more points. It intersects the graph in an infinite number of points and is therefore not one-to-one. So the answer is no. Any questions on this particular topic, the horizontal line test? So
when do you know whether to use vertical line test or horizontal line test?
the horizontal line test checks to see if your graph of a function is one-to-one. Vertical line test is to test if you have a function. And you're not going to be doing problems on that. You're only going to be doing problems on the horizontal line test. So vertical line test is that if you have a graph, you want to see it, is that graph a function? That's when you use the vertical line test. Now the horizontal line test, you have to have a function to use the horizontal line test. So the horizontal line test is to test to see if that function has that nice one-to-one correspondence, like we saw back here. Okay?
All right, thank you.
You're welcome. Any other questions before we move on? So functions and their inverses, which are also functions, have many nice properties. How do we determine if two functions are inverses of each other algebraically? That's what this topic is about. Determining whether two functions are inverses of each other. For each pair of functions, f and g below, find f of g of x and g of f of x. Remember, we need to be able to take the composition in both directions, get back x, in order for us to have functions that are inverses of each other. So this needs to give us x, and this needs to give us x. And if we do that, then we're going to be able to determine whether our functions are inverses of each other. If we get both of these to be x, they are inverses. If one of them is not x, then they are not inverses. And we'll see both situations in this problem. Simplify your answers as much as possible. Let's do part A first. Part A, f of x is 3 divided by x, and of course they had to make the statement x can't be 0 since the entire denominator can't be 0, because then we would get an expression which is undefined. And coincidentally, g of x is also 3 divided by x. So let's look at what we're trying to find first. We're trying to find f of g of x, and we work with the inside parentheses first, right in here. So we want to find g of x. We actually want to find the whole thing. So let's write it out as f of g of x like this. Now, we want to go inside and figure out what g of x is first. G of x is given to us as 3 divided by x. So we're going to take out g of x only and replace it by 3 divided by x. Now, what do? We have to go to our f function. What's our f function say? We take what's inside the parentheses here. And what do we do with that? We take 3 and divide it by what's inside the parentheses. So here's the 3, And we're going to divide it by what's inside the parentheses here, which is 3 divided by x. So now what? We have what we call a complex fraction, but not to worry, it's not too bad. This fraction bar is really a division sign. We want to multiply and invert. Well, how do we do that? First of all, we copy down what's above this fraction bar first to get the 3. Then we change to multiplication, which is understood here. And then we want to invert, which means flip over this 3 over x. 3 divided by x, if you flip it over, you get x divided by 3. Now these 3's cancel, and we're left with just x. So this right here is x equal to x. And remember, in order to have functions which are inverses of each other, we need both of these to give us x, both of these, not just one of them, both of them. Any questions on this first part of part A where I just found f of g of x? So let's do the other one now. We need to do g of f of x. Copy that down. We first need to go inside these parentheses here and find f of x. F of x is just 3 divided by x. So took out f of x and replaced it by 3 divided by x. Now we need to find g of this input here, g of what's inside the parentheses. What does our g function tell us? Whatever inside the parentheses, it ends up in the denominator over here. So first we have to copy that 3 down. And then whatever's inside the parentheses here goes in the denominator. That's what it's saying. Whatever's inside the parentheses goes over here as in the denominator. So we have 3x, so that ends up in the denominator over here. We have 3 over x, so 3 over x ends up in the denominator here. And really what you're seeing here is you have exactly here 3 divided by 3 over x. And here it's exactly the same, 3 divided by 3 over x. So we're going to get the same answer here, x. So for g of f of x, the answer is just x. So both of the compositions, their direction are x. That means the functions are inverses of each other. And what really is happening, it says the functions are inverses of each other because first we find g of x and then we find its inverse and we get back where we start. So we're starting with x. First we find g and then we find f and we get it back exactly what's in parentheses here. The same thing here. First we find f of x and then we apply the g function. We get back whatever's in parentheses here, which is x. It could be 5, it could be 3 plus 6x, whatever in parentheses. We're going to get back what we started. Or we're actually going to get back x if we apply a function and its inverse. So f and g are indeed inverses of each other, so I colored in this answer here, or colored in the circle there, that corresponds to this. Now I want to do my due diligence and show you an example where the functions are not inverses of each other. Let's look at B. F of x equals x plus 4, g of x equals negative x plus 4. Sometimes students think those are inverses of each other, but they aren't. So let's start with f of g of x. So I'm going to go down here, part B, f of g of x. Take out g of x and replace it by what it's equal to. G of x is negative x plus 4. So we're going to take out this g of x, replace it by negative x plus 4. And this is what we have so far. So this is what's inside the parentheses. What do we do in the f function? What does the f function tell us to do? We take what's inside the parentheses and do what? Take whatever's inside the parentheses This is what's ever inside the parentheses, and add 4 to it. So inside the parentheses, we have negative x plus 4. We want to add 4 to that. That gives us negative x. 4 plus 4 is 8. Now, what do we have to be able to have two functions of which are inverses of each other? We have to get back x. We do not get back x. And we have to get back x twice when we find this composition and this composition. Well, we didn't even get back x here. So there's no way we're going to get back x twice because we didn't get it back for the first composition. So the answer is, since we did not get x, the answer is f and g are not inverses of each other. So if you try the first composition and you're confident that you didn't get x, then you can state automatically at that moment f and g are not inverses of each other. Any questions on this problem, on these two problems that we actually did? So let's go on. I may want to do this one. This one looks an awful lot like the one we just did. Let's look at this one. Yeah, I just want to take a quick peek on this one. Let's do at least one of these. Okay, I don't have time to do both of them. Let's do the one where I want to see it's x minus 1 plus 2. I think let's do the second one. Let's do g f of x here. Okay, so when we do g f of x down here, this last one, we first want to go and get our f function. What's inside here? Our f function is 2x plus 1. So I'm going to take out f and replace it with 2x plus 1. Now what do? We go to our g function now. And what do we need to do? What does our g function tell us that we do when for whatever's inside the parentheses? What do we do to what's inside the parentheses? That's our x. We subtract 1. Whatever's inside the parentheses, we subtract 1 and divide by 2. So what's inside the parentheses? 2x plus 1. And we need to do what? Subtract 1 and divide by 2. That's what it's telling us up here. Subtract 1. Whatever's in parentheses, subtract 1 and divide by 2. So after we do that, 1 minus 1 is 0, plus what's left is what's left, which is 2x. These 2's cancel. We just get x. And this one works similarly, and you're going to get back x. And since both of these give us x, they are indeed inverses of each other. Okay, any questions on that? I want to make sure you saw some of that. Another one of those problems. I did one of those problems in this topic because I wanted you to see it again. Let's go on. This is a great problem. So the one-to-one functions g and h are defined as follows. G is given to us as a set of ordered pairs. H is given to us in more algebraic notation here. And we're actually asked to find the following. G inverse of 2. In other words, what's the output? What's the y value when x is 2? X is in parentheses. We're asked to find the inverse function of h, which is up here. And we're asked to find this composition, h inverse composed with h. Now, what we've learned so far is if you have a function and its inverse, and we know that we have a function and its inverse because they're using this inverse notation right here, you get, no matter which, when you take the composition in either direction, you get back with what you start. what do we start with here? We started with -3. When we do this and write it in workable form, and we do what we need to do, we're going to get back -3 here. So you get back what you start with. That's the beauty of a function and its inverse. So that's easy. There's no work to show for that. That's like, hey, I know what, I know if you apply H and then you apply H inverse, or if you apply H inverse and then H, you're going to get back what you start with, -3. So that one should just be write it in. So we need to do these other two here. What I would recommend for G inverse is you take your G set, this G set, and what do you do to get the inverse? You just switch all the X's and Y's. So this -5, comma -2, you switch you put this Y goes first, which is -2 over here. This X goes last, which is -5. And you do that for each ordered pair. Change the X and Y coordinates. For this last one, this Y2 is going to go in for X here. And this X of 9 is going to go in, that 9 is going to go in for Y over here. What to find? And also, this is the function G representation. This is G inverse because we switched all the X and Y's. What are we asked to find? G inverse at 2. So you go over here. This, what's in parentheses here, is your X. You go over here until you find an X of 2. I'm looking. Here's an X of 2. What's this Y coordinate? It is 9. This G inverse represents Y. So we're looking for the Y coordinate when X is 2. So our Y coordinate is 9. So that one's not too bad. Now we need to do some algebra to figure out what this answer is. So we want to find H inverse of X for this function H. So we're going to copy down our function. Now we don't need to copy down H of X. We can do the first step, and the first step to algebraically finding the inverse is to replace H of X by Y. Take this H of X out, put Y in its place, and just copy this right side down. Now the key step is to replace Y by X and X by Y, because that's what happens in the inverse. Those get switched. So here's Y, I'm going to replace it by X. Equals negative, here's X, I'm going to replace it by Y. Minus 14 divided by 11. Now we're going to solve for Y. So what do we do first? We want to get the Y by itself. Let's first move the 11 to the other side. It's participating in division over here. So let's the opposite is multiplication. Let's multiply both sides by 11. So we're going to get 11x over here because we already have an x equals 11. And I just copied this down and put it in parentheses right here. These 11s cancel. 11 divided by 11 is 1 times what's left is what's left, which is this, minus Y minus 14. And we have 11x that I just copied down on this side. Now we want to solve for Y. To do that, since this has a negative in front, I want to move it to the other side to make it positive. I don't like dealing with negatives, especially if I see something else with a minus sign in it. So I find it easier just to add Y to both sides. That's what I'm doing here. And what do we get on this side? We get Y plus this 11x. These cancel, equals minus 14 on this side. We want to solve for Y. So we're going we have adding 11x, the opposite is subtracting 11x from both sides. This is going to give us 0x plus y is y. And on this side, we have a negative 11x minus this 14. We have now solved for y. And lastly, we want to replace y by h inverse of x. So we take out this y, we put in h inverse of x notation as well. And so we can go back up here, put that in, and we're done. You'll know if you really understand inverses if you can do this problem or get this this particular topic correct by getting 3 in a row right. Any questions on this particular topic? That is really the easiest way to do it. Sometimes we do see inverse function notation written like this, f composed with f of -1 of x, and we write it rather than with f and g, we use this. So I think we've seen that, we have already seen that with h and h inverse. So now let's take a look at another written work problem that you're going to see on your second test. And there could be I'm going to do 2 of these because you could see either type. So it's important to know how to do both types. Inverse function, cubic and cube root. The one function is defined below. F of x equals the cube root of 7 minus x plus 6. So we want to find f inverse of x, where f inverse is the inverse of x. So we start by taking out f of x and putting y in its place. That's what I did in the first step, just took out f of x and put y in its place. If you I want to see, it's always better to show too much written work than not enough. I have to be able to clearly to identify your process. So if you're trying to do 2 steps in one, I might not be able to identify your process. So it's better to show all the steps that I'm showing. So I would encourage you to do that. If I have a doubt, I'm not going to give you full credit. So I'll probably take off for that. It's important that you learn to present well in every subject that you study in college, because math presentation skills, if you're going into the business world, I can assure you they're likely to come up. So particularly in other disciplines as well. So let's take out, again, this f of x and replace it by y. Now the next step is really critical. You want to replace y by x and x by y, which have been done here. And then you want to solve for y. Well, the first thing I want to do is move the 6, the opposite of addition, subtracting. So let's subtract 6 from both sides. That leaves us with x minus 6 on this side. Plus 6 minus 6 is 0. Plus what's left is what's left. So now we're down there. So what do we do next? We have the cube root. The opposite is cubing. So we want to cube both sides because we want to get that y out from underneath the cube root. So let's cube both sides. So we put this side in parentheses right here, and cube it. We put this side in parentheses and cube it. Cubing undoes cube rooting. So on this side, we have just left 7 minus y, and I just copied down this side. We want to solve for y. I don't want to move the negative over here because then I'm going to have negative y. I mean, I guess that would be okay. I just generally like to, as long as you do it correctly, which is very important. No, what I'm saying is, no, what I don't want to do is move this -7 over here. Then I'm going to have a -7 plus this equals a negative y. That is a little confusing to me. So what I like to do personally and you can do it the other way if you, as long as all of your written work is correct, and I can read it all, is you could leave the negative y here. I chose not to do that because I feel like it's more difficult somehow, and I feel like I'm not as likely to be 100% accurate. So it's up to you. So as long as you're 100% accurate, you can get quite possibly get full credit for the problem. So that's what you want to do. And you have those choices there. But I want to make this whatever is in front of y positive, because that's what I am solving for. And I find just with other types of problems throughout math, I find that serves me better and causes me to be more accurate. So I'm going to add y to both sides. I get y plus this, just copy down, equals, these cancel, 7. These y's cancel here, 7. Now, I want to move this because I want to get y by itself. We've got an addition sign in front. What I don't want is a minus sign in front. So, got an addition sign in front, the opposite of subtraction. And if you get a minus sign in front, you better make sure that's all it is. It is quite difficult sometimes to work with problems depending on how you do them. I would just, the moment I know I have a positive y, I feel fine. I feel better. So that's all I'm saying. So the opposite of adding this expression right here is subtracting that entire expression. If I subtract this entire expression from this side, we need to do it to this side as well. That will leave us with just y on this side. And on this other side, we have 7 minus this. And now I'm going to take out the y and put back in the inverse notation. And that's how I finish this up. And that is the correct answer. Any questions on this particular problem? So you could see one like that on your second test. It's almost hard to believe that we're almost halfway through the semester. I don't know where the time went. So any questions on this one? I do want to take a look at a different one. So what you see here is a cube root function. You could also see for this topic a cube function. So let's see that. Let's look at this problem, same topic. And you're going to see one of these types on your second test, and it's a written work problem. So we're going to start with this, f of x equals 2 minus x cubed. First step, take out the f of x and replace it by y. Just copy down 2 minus x cubed. The critical step is replacing y by x and x by y. And now we want to solve for y. So let's solve for y. I like to have a positive plus sign in front of y. So I am going to move this y cubed to the other side. The opposite of subtraction is addition. So I'm going to add y cubed to both sides. That will give us x plus y cubed on this side equals 2, this 2 right here, minus y cubed plus y cubed is 0, 2 plus 0 is 2. So that's all we have at the moment. So we want to solve for y cubed, because that's going to allow us to solve for y. So let's solve for y cubed. The opposite of adding x, subtracting x. Let's subtract x from both sides. X minus x is 0, plus what's left is what's left, and that is y cubed. And on this side, we have negative x plus 2. We just tend to write it in that order. So right now we've got y cubed. The opposite of cubing is cube rooting. So we want to cube root both sides. Please make sure you know how to write down a cube root. You need to have that 3 and that v. We don't do it for square roots, which are really a 2, because we use them so often. But we know the default for square roots is a 2. If we leave this undone, without a 3 here, then I will assume it's a square root. So That's how mathematicians think. So this is we take the cube root of both sides because cube rooting undoes cubing. What we do to this side, we have to do to this side. So we want to take the cube root of this. So we have the cube root of negative x plus 2. So what do we get? Cube rooting undoes cubing. So we just get y on this side equals, just copy this side over, take the y out, replace it by the inverse notation. So our answer is, on the right side, we need cube root of negative x plus 2. So cube root of negative x plus 2. Any questions on this particular topic? So you could see one or the other types of problems from Alex on your test for this particular topic. Please be sure you practice a few of each, knowing that they're written work topics. I had a student who got almost every one of the non-written work problems correct, but did not get I think he got but a couple points on the written work topics, and that's worth half the test. Those written work topics, 7 of them times 7 points apiece is worth 49 points. And they're really important. Because in all likelihood, I can't guarantee it, but in all likelihood, most of the written work problems on the final are going to be ones you've seen already. So it's important. You want to make sure you're preparing yourself as you go through the course. The knowledge checks are to prepare you for the tests. The tests are to prepare you for the comprehensive final. And you can't assume you're going to retain the material unless you are taking steps in the course to retain the material, like studying for the knowledge checks as if they are tests. So I encourage you all to study for retention. Let's take a look at this particular problem. We're not actually going to do one of these in Alex because I think you're all familiar with this. Below is the entire graph of function f, graph f inverse. Well, just like we've done before, you want to find all the corner points and all the endpoints or corner points on your graph. And you could call them all endpoints if you wanted to. Here's our given graph. We want to find all those ordered pairs. So I found them and wrote them down from left to right, it looks like. -4, -6, and we all know how to find ordered pairs. We've spent a lot of time on that in class. 0, 2, 4, 3. Now, this is the x coordinate. This is the y coordinate. What is Alex asking us to do? Graph the inverse. Well, what's the main step but how do we get from a function to its inverse? The main step is to switch the x and y coordinates. So we take all of these x coordinates, -4, -3, 0, 4, and we switch them to the y coordinates. We take all of these y coordinates, -6, 0, 2, and 3, and we switch them to the x coordinates. And that's what we do. Then we plot all of these ordered pairs in Alex, and then you use this tool to connect them from left to right, and you've got your graph. That's all there is to this. So any questions on this particular topic? These last two problems have to do with I'm actually not going to do this one because I think it's pretty self-explanatory. I'll come back if we have time. Let's do this last one. We're talking about the graphing calculator here. So if you have your graphing calculator handy, you probably want to do this along with me. If you notice here, we've got E here. So this is really, maybe I'll write down this first one bigger so you can see it. The first one is E raised to the negative 0.5 hard to do a point here, negative 0.5. So that's what we're finding using the calculator. That right there. And that's supposed to be 0.5. Sorry about it, it's a little off. So we want to do that on our calculator. That's because we're getting ready to study logarithms. And how do we do that? So let me show you on the calculator here. I've got one up here. See if I can bring that a little closer here. So where we go to get E on the calculator, in this first column, if you go to the third button up, E to the X is above the ln key here, the natural log key. It's right there. It's right there. It's in that first column, third button up. However, it's actually above the button. So in my calculator, it's in blue. So I have to use the blue key first, the second key. So to get E, I need to use the second key first. Click on my calculator that actually works. This one doesn't work, it's just a picture. So I want to go to my actual calculator that works, and I want to clear off my screen, and I want to access this E, which is a non-terminating, non-repeating decimal like pi. It's actually a number. To access E, I need to first click on the second button and then click on this ln button right there. And that will give me E to a box, and I can put whatever I want in that box. What I want in that box now is a negative. Now, when we're talking about a negative, we're talking about a negative in the bottom row here of this calculator, right in the bottom row here, that negative. I want to click on that negative. I don't want minus here, I want negative. And then type in point, which is in the bottom row, right here, 0.5, and then enter. And I get, and we're rounding to the nearest thousand, I get 0.606, but the next digit is a 5, which means I want to bump that last 6 to a 7. This is tenths, hundredths, thousands. So that's what I get. This one down here is just a matter of practicing another problem. So let's practice that problem. 260. Okay, so 260 times E to the 0.25 times, so I'm clicking on the multiplication button over here in the rightmost column, E, so that's second ln, get a box, and in the box put 0.25. And we're still rounding to the nearest thousands. 3 places past the decimal point. If you see here, if you read 3 decimal places, that means 3 decimal places past the decimal point. So this is 333.846. Next digit is a 6, which is 5 or higher. So that 6 I need to bump to a 7. That will give me 333.847, which is what I got right here. Any questions on this particular problem? And like I said, and one thing I'd like you to do, just to be sure, is what is E equal to? Just E to the first. What's the number E equal to? So if I want to find the number E, I can go to my calculator, do the second ln, and in that box put the number 1. That's just going to give me 1E. It's not going to give me, remember, E squared would be E times E. E cubed would be E times E times E and so forth. But E to the first is just E. And if you hit enter, you will get an approximation for what E really represents. E represents a number, but it's rounding on the calculator. 2.718281828. It comes up a lot in application problems and in nature. Radioactive decay, carbon dating, population growth. Population could be anything. It could be people. It could be number of cells in somebody's body. It could be rabbits. It can be money, population of money. So there's a lot of places with where this E comes up. It's quite, and like with pi, it's quite remarkable that they come up like that. So it's really, really neat. So I wanted to speak about that. I think on the problem that we looked at right before that we skipped over, it's one thing I do want to talk about. And why don't we do this one right here on our calculator? Find the price in dollars, that's what that stands for, when time is with 10 years. So all we're going to do is take 10 and plug it in for this T here. So we want to do this problem. It would be very wise for you to do it. What we have here, and then we'll, just so you can see what this is. Right up here, this is really a T. Let me try it a little bit bigger. Maybe if I can put it here, that I got to remember that trick to like put a little dot somewhere so I can see what I'm doing with the first mark I make. I've discovered that trick. I just don't use it enough. And I just had got rid of both of them, which was certainly not the intent. So let me put a little dot somewhere over there. And then I can put my big T here. Okay. So what I want to do, no, I don't want to get rid of that, is we're really raising to the T. I'm not sure that you can see that that's a T up here. So when the price, we want to find the future price is really what we're finding when T is 10 years. And to do that, we're putting in 10 for T up here in the exponent. So you could find that on your calculator. It would be 600 times parenthesis, because there's parentheses around this, 1.022 1.022 parenthesis. Now, where do you get, how do you raise to the T? Does anybody know how we can raise to the T and explain it to me? Does anybody know? Mountain peak over here raises to, that's how you raise. You go up. You go up a mountain. You go up to get the exponent. That's how I think about it. That's the mountain peak over here. So you want to click on the mountain peak key. The mountain peak key is in the rightmost column. That will give you the ability to enter an exponent. For that exponent, we want to put in 10. And if you round it to the nearest dollar, I get 745. The first digit past the decimal point is 8, which is 5 or higher. So that 5 before the decimal point, I have to bump to a 6 and get $746. Now, one more thing I want to mention is when they ask for the current price, they're asking for the price right at this split second, right now. And at this immediate time, right now, the time that has gone by is 0. So that's why you have a 0 up here in the exponent. So when you mountain peak that, you want to put a 0 there. So I have covered this objective today. I've covered everything in here that I want to today. So this ends the material that test 2 will cover. Test 2 will cover everything from test 1 to what we covered today. So I will come back up there and I will ask you if you have any questions. Do you have any questions that you want to ask me? So let me, anybody have any questions? Well, I want you all to have a great weekend. Please stay healthy and safe and take great care of you and your loved ones. And I will see you on Tuesday in our remote class. I will be sending Canvas announcements. I will be posting some Canvas announcements tomorrow, so please be on the lookout for those. Yes, the test 2 is 1 week from today. You can look that up, and if you don't remember, you can go on the main menu and Alex to the calendar. So feel free to leave this conference if you want to stick around and talk with me. I'm free right now, so feel free to stick around and talk with me if you have any questions. Take care. I will see you next time, which will be Tuesday in our remote class. Bye for now. Thank you, Jacob. Thank you. You're welcome. You're welcome to all of you. Anybody have any questions? Courtney, do you have any questions?